Well, welcome to the third lesson of Activity 22. We are on lesson 22-3, now using trigonometric ratios. In the previous lesson, we learned what those ratios were, so let's just recall when we use the term sine, and again we use S-I-N, when we use the term sine, we are referring to the opposite leg of an angle compared to the hypotenuse of that triangle. And cosine, again, we use COS to represent cosine. We are writing a ratio comparing the adjacent leg of an angle to the hypotenuse of that triangle. And then last, tangent, which again we use TAN for tangent. We are comparing the opposite leg of an angle to the adjacent leg of that angle. So just keep that in mind. And so we define what those trigonometric ratios were, and now we are going to use them. So let's see what we're using them for in our learning targets. So we are going to use trigonometric ratios to find unknown side lengths in right triangles. If you haven't noticed, over the last few activities, we've really been discovering new ways to find missing sides of right triangles. We learned about similar right triangles and how their sides are proportional, so we could write proportions to solve for a missing side. We learned that if we had 2 out of the 3 sides of a right triangle, then we could use the Pythagorean Theorem to find a missing side. And now we're exploring how we can use trigonometric ratios to find unknown side lengths. Then we are going to solve real-world problems using those ratios. So we're going to put that information into some real-world context to see where this stuff exists in our lives. So if you would, go ahead and draw a line right above 2. We're going to chunk item 1 for starters. So read through the text, complete item 1 before playing through. Okay, so as we dive in, let's notice a couple key things here. They're asking us to determine the ratios requested. That's really what we're doing. We are finding the sine of 41 degrees, and we're finding the the cosine of 28 degrees. It says then use a scientific or graphing calculator to evaluate each trigonometric function to the nearest 1,000. So we're going to use Desmos to find out the approximate value of the sine of 41 degrees and the cosine of 28 degrees, and we're going to round those to the 1,000th place. As many decimals as we can use, the closer to the exact value that we are, without being too ridiculous. And then we're going to solve each equation for y and round our final answers to the nearest 10. So let's take a look at what we actually have on item A, and why knowing these trig functions can actually be pretty amazing. Right off the bat, when you look at item A, you should notice that although we have all the angle measures, we only have one length of a side, which in this case is the hypotenuse, which is pretty profound because up until this point, we've actually needed more than just one side to find other sides of a right triangle. But by studying these trigonometric ratios and knowing that if we have another right triangle with an angle of 41 degrees, that when you compare the opposite side of that angle to the hypotenuse, it's going to be equivalent for this triangle as it is for any other right triangle that contains a 41 degree angle. So on item A, they ask us to find the sine of 41, and I'll tell you the main reason why, pun intended, is if we're looking for this side, RQ, which is opposite of 41 degrees, and we are given the hypotenuse, which is 100, it should make sense in our minds that we would use this trig function, the sine function, because we're looking for the opposite side of 41, and we are given the hypotenuse. Now, because we have the 49 degree angle as well, we could have also used the cosine of the 49 degree angle when looking for the adjacent side y compared to the hypotenuse, which is 100. And remember, the sine and cosine of complementary angles are equivalent. So we could have used sine of 41 here or the cosine of 49. So they asked us to round that trig ratio, sine of 41 degrees, to the nearest thousandth. So I'll show you that over here on Desmos. So the sine of 41 degrees is 0.6560. The second 6 is actually the thousandths place. So we look to the 0 to tell that 6 to stay where it is. So I said that the sine of 41 degrees is roughly 0.656. So here's the ratio we have. The sine of 41 is the opposite side of 41 degrees compared to the hypotenuse of that 41 degree angle. So I had the sine of 41 degrees equals y over 100. And notice what I did. I replaced sine of 41 degrees with that approximate decimal 0.656. And then one method I showed you here for solving this is that if we're trying to solve for y is being divided by 100. So to undo that division, we can multiply both sides by 100, and 100 times 100 divided by 100 is 1, so it would be 1y, and 100 times 0.656 is 65.6. The other way you can do it is you can then write it as a proportion, and it goes back to what we're really studying here and how these similar right triangles are proportional. So again, I replaced sine of 41 degrees with 0.656 equal to y over 100. And then, strangely enough, I wrote 0.656 over 1 because you can write any number over 1 because it does not change the value of that number. And then I simply cross-multiplied. Y times 1 is y, and 100 times 0.656 is 65.6. So there's two methods there, and I'm actually going to heavily rely on this method as we move forward. But I did want to show you that that method is also valid. So let's look at item B. They tell us to use the cosine of 28 degrees. And again, that's a great trig function to use here because in reference to the 28 degrees, we have the adjacent side, which is NO, and they tell us that length is 18. And we're looking for the hypotenuse, which is MO, and they label that Y. So we have the adjacent side to 28, and we're looking for the hypotenuse of that right triangle. So it makes sense that we would use the cosine of 28 degrees. Again, you could also use the sine of 62 because we would have the opposite side of that 62 degree angle, and we're looking for the hypotenuse. But again, the sine of 62 is the same as the cosine of 28. So regardless, both trig functions could work here. So the cosine of 28 degrees is the adjacent side, which is NO, which we've established as 18, over the hypotenuse, which what we're looking for, y. So again, I plugged in cosine of 28 degrees in my Desmos graphing calculator, and I found that it's 0.8829, and that 9 actually tells my 2 to round up to a 3. So the decimal approximation for cosine of 28 degrees is 0.883. So I'm going to replace cosine of 28 degrees with that decimal approximation. And just like that second method I showed you down here, I put 0.883 over 1 to write a proportion, and then I cross multiplied. Got 18 times 1, which is 18, 0.883 times y, which is 0.883y. And then to undo this multiplication here so I can solve for y, I divide both sides by 0.883 and found that y equals 20.4. So we're actually using these trig ratios to find missing measures of sides when we are only given one side length to begin with. So it's pretty remarkable how we can use these trig functions and these angles to find missing sides of right triangles. Now we're going to chunk item 2. So go and draw a line right at the very bottom of the page to A through E and complete item 2 before playing through the video. So hopefully you took a minute to work through this, and I'm actually going to show how to find this missing side, the value of x, using either acute angle, and really stress what we've been trying to make known over these last few lessons of how the sine and cosine of complementary angles are actually equal to one another. So this number 2 is actually, sorry about that, caught me off guard. Item 2 is actually a great way to determine what trig function to use to find a missing side. And I roughly kind of explained that here on item A and B, why they chose sine of 41 and cosine of 28 because of the information that was given. So looking at angle C, if angle C is our indicated angle, which is our 20-degree angle, the opposite side is AB, the adjacent side is BC, and the hypotenuse is AC. And remember, the hypotenuse is always going to be opposite of the right angle. So the hypotenuse will always be AC in this right triangle, regardless of which angle you're looking at. So with that in mind, looking at angle A as the indicated angle, opposite side to angle A is BC, which notice is the adjacent side to angle C. This is why the sine and cosine of complementary angles are actually equal, because the opposite and adjacent sides switch. So the adjacent side to angle A is AB, and the hypotenuse, again, as stated, is AC. So it says use the sides to choose an appropriate trigonometric function. So if we're focusing on angle C, we're looking for the opposite side, and we're given the hypotenuse. Which trig function uses the opposite side compared to the hypotenuse? Well, the sine function. So we're going to use the sine of C. But if you're looking at angle A, and if A is the indicated angle, we're looking for the adjacent side, and we're given the hypotenuse. So you could use the cosine of A. And to really emphasize how the sine and cosine of complementary angles are equal, let's see what happened on item D. So item D said write an equation using the identified sides, acute angle, and trigonometric function chosen. So the sine of C is the sine of our 20-degree angle, and it is the opposite side, which is AB, which we will call X, and 15, the length of the hypotenuse. Well, I went over to Desmos and I actually calculated the sine of 20, and the sine of 20 is 0.342, rounded to the nearest thousandth place. So I replaced sine of 20 with 0.342 equal to x over 15. And then using this method here, I put 0.342 over 1 and use cross multiplication to find that x equals 5.13. Well, if you notice back on that Desmos slide, if you used angle A, the first thing you had to do was actually find angle A. Well, if these two angles really are complementary, and this angle is 20 degrees, then 20 degrees plus what is 90? Well, it's 70 degrees. So you could have done the cosine of 70 degrees, and notice what I got when I put cosine of 70 degrees in our graphing calculator. I got the same as the sine of 20. What we're emphasizing is the sine and cosine of complementary angles are equal. So notice I can replace cosine of 70 with the same decimal I replace the sine of 20 with. And I cross multiply here, and I get the same conclusion, that x is 5.13. So this is a great way to establish which trig function you're going to use to find a missing side. And you don't have to use both, just wanted to show you that both could work. So now let's repeat that process. Hopefully now that we're getting the hang of it a little bit, repeat that process on item 3. So let's chunk item 3, A and B together. So complete item 3 before playing through. Now hopefully we're getting a little more comfortable with figuring out which trig function to use. So item A said choose an acute angle in triangle DEF. And again, I'm splitting the choices here. You could have chosen angle F, and I imagine the majority of students, and it would make sense, go ahead and use angle F because we already know the measure of that angle. You know, to use angle E, we actually have to find the measure of angle E. So for testing purposes, by all means, if you're given angle F, use angle F as your acute angle. So in reference to angle F, side opposite of angle F is side DE. Adjacent to angle F is side DF, and the hypotenuse, and again, it's regardless if we're looking at angle F or E, the hypotenuse is segment FE because it's opposite of the right angle, which is located at vertex D. So if you used angle E just because you wanted to be wild and crazy here, opposite of angle E is line segment DF. Adjacent to angle E is side DE, and hypotenuse to angle E is again still EF. Now I didn't work through this one entirely because you notice it's actually the same work. So if you decided to use angle F, then you should have used the cosine of angle F, and I'll tell you why. because we are told the adjacent side to angle F, which is side DF, and we are asked to find the length of the hypotenuse, EF, which is labeled Y. So we know the adjacent side, we're looking for the hypotenuse, and so the best trig function uses adjacent over hypotenuse, which is cosine. So the cosine of F is the cosine of 10 degrees, because that's the measure of angle F, 10 degrees, and it's equal to the adjacent side, which is DF, which is a length of 12, over the hypotenuse, which is a length of Y. So we evaluated cosine of 10 to the nearest thousandth. I'll show you here. So the cosine of 10 is 0.9848, and the 8 rounds the 4 up to a 5. So I used, instead of writing cosine of 10, I replaced it with the decimal approximation, 0.985. And then, using the method that I'm trying to stress to you, I wrote this side as a ratio, writing it over 1, and then did cross multiplication. 12 times 1 is 12. 0.985 times y is 0.985y. And then to solve for y, I divide both sides by 0.985 and find that y is 12.2. Well, back on the Desmos slide, you might have noticed that I also found the sine of 80 degrees, the complementary angle to our 10 degree angle there, and you see that it's also 0.985. So if you decided to do angle E, hopefully you chose the sine of E, because again, looking at angle E, we have the opposite side, DF, which is 12 units, and we're looking for the hypotenuse, EF, which is y units. Well, the sine of E, angle E would have to be 80 degrees, because 80 plus 80 degrees is the complement to our 10 degrees. And notice, when I replace sine of 80 degrees with 0.985, I have the exact same equation. Again, just stressing that the cosine and sine of complementary angles are in fact equal. So you don't have to use both angles here, just showing you that they would work. So hopefully now we're seeing the usefulness of these trig functions, why we learned sine, cosine, and tangent, and how to actually use these trig functions to find a missing side. Sorry about that. Now let's put all this work into some real world context, our second learning target. So we are going to chunk item 4, which is A, B, and C. So if you would go and draw a line at the bottom of the page here, and then pause the video and complete item 4 before playing through. So now that you've had the opportunity to put trig functions in real world context, let's just notice a couple things we should have highlighted along the way. So there is a ladder, and it's actually a 12-foot ladder. So that's going to be one of our measurements we need to pay attention to. And it says when she puts the ladder up, it makes an angle of 75 degrees with the floor. And that's actually really important that we label that correctly. So in the original diagram, here's my 12-foot ladder leaned up against this wall, and it makes a 75-degree angle with the floor. And of course, we assume that the wall and the floor make a 90-degree angle, so we are dealing with the right triangle here. So B says, set up and solve an equation to find how far up the wall, and notice I went from the top of the ladder to the bottom of the wall, how far up the wall the top of the ladder reaches. So I called that side X. So think about what we've been saying the last two problems in reference to the angle we know, and of course you could find that one if you're crazy enough to do that. In reference to the angle we know, the 75-degree angle, we are looking for the opposite side, and we are given the hypotenuse. So it should make sense that the easiest route to take is to use the sine of that 75-degree angle. So the sine of 75 degrees is opposite x over hypotenuse 12. Now I went and plugged in sine of 75 in my graphing calculator and found that it was 0.9659, so it'd be 0.966. We're just going to keep rounding to the nearest thousandth, even though they didn't tell us to do that. It's just a smart idea, just so we're exact as possible. So I replaced sine of 75 degrees with 0.966, and so I got 0.966 equals x over 12. And I wrote this side as a ratio over 1, and then did cross multiplication to find that x equals roughly 11.6 feet. So the height of my wall is, or that the ladder reaches on the wall is 11.6 feet. And then what I love about C is that they give you two options here, because now we actually have the height that the ladder reaches on the wall and the hypotenuse of our triangle. So we know two measurements of this right triangle, so we can use Pythagorean theorem to find the third. Just because we're not learning the Pythagorean theorem in this lesson doesn't mean we can't use it, because now we have two of the three sides of our right triangle, so let's use it. Now, they also want us to show using another method, so I just use the cosine of 75 because now we're trying to find the distance from the base of the wall to the ladder, which in reference to this 75-degree angle, this side right here is our adjacent side. So I have the adjacent side. I already knew the hypotenuse, so cosine should make sense. Now, could you have done tangent now that you found the height of the wall? Sure. But 11.6 was a pretty approximated answer. So I always encourage you to use the information that was given from the start. Use the information that wasn't rounded. So that's why I chose to do cosine of 75, because it would find the length of this side and use the hypotenuse that was already given to us. So if you notice, I found the decimal approximation of cosine of 75, which is 0.259. So I replaced cosine of 75 with 0.259. Wrote it as a proportion and cross-multiplied and solved. And then I also used the Pythagorean theorem because, again, because we found the height that it reaches on the wall and the hypotenuse, we now have two sides of our right triangle. So remember, the ladder in this instance is acting as the hypotenuse, so we should plug that in for variable C in the Pythagorean theorem. Now, the height on the wall doesn't matter if it's A or B, so if you plugged in 11.6 for A, please don't worry there. We're just finding this measurement on the right triangle. Square first. So 11.6 squared is 134.56. 12 squared is 144. Subtract this value, 134.56, from both sides, so we can get A squared by itself. And we get A squared is 9.44. Now, to get rid of this square, we take the square root, and we get that same approximate value, 3.1 feet. So now we can see how the trigonometric functions really come into play here, especially from the beginning, we only knew the height or the length of the ladder. And so we were able to use the trig function to find the height that it reaches on the wall and the distance it is from the base of the wall. Again, because these lessons do have some heightened complexity, I am going to look at the check your understanding with you. So let's go in chunk 5 and 6. We'll just complete those on our own before playing through the video. So the check your understanding didn't actually want you to find anything. For example, on number 5, it just wanted you to explain how you could find it. Really start processing how to use these trig functions. And notice it said without the Pythagorean theorem. And I would argue that you definitely can't use the Pythagorean theorem to find the length of DE because we don't have enough information. So I said I would use the cosine ratio with the given measure of angle E, 25 degrees, and EF being 16 feet to find the length of DE. Because if I'm looking at angle E, EF is my adjacent side and DE is my hypotenuse. So I could set up the equation cosine of 25 equals 16 over x. Now they didn't actually want us to solve, but of course you're more than welcome to. Then item 6, again, notice there's no solving here. It says Joe says she can find BC using the equation sine of 40. So she is assuming that in reference to the 40-degree angle, BC is the opposite side, which Joe is correct, and 62 is the hypotenuse, which, again, Joe is correct there. Liam says that he can find BC using the equation cosine of 50 degrees. Well, if you're asking yourself, where is the 50-degree angle? Hopefully you know now it's here at angle B, because if this angle is 40, this complement has to be 50. And so Liam says I can use the cosine of 50 because BC is the adjacent side to that 50-degree angle, and Liam is correct there. And AB is the hypotenuse to that angle. And again, Liam is correct there. So who's correct? They're actually both correct, because notice Joe is using the sine of 40 and Liam is using the cosine of 50. the sine of complementary angles are equivalent. And notice, look here. In fact, they are. The ratios are the exact same. So Joe and Liam are both correct because the sine of 40 is equal to the cosine of 50. Just further stressing how the sine and cosine of complementary angles are equal. So that is the end of lesson 22-3, applying and using those trigonometric functions. And we even got to see a little real world example there in item 4. As always, complete the lesson practice. It's great practice. And go back and reevaluate your learning targets. Thank you all for watching.